Hello, students. Have you ever wondered why the smell of vanilla or cinnamon feels so sharp and distinct? The answer lies in the reactivity of carbonyl groups present in aldehydes and ketones. Let's begin our journey with nucleophilic addition. The carbonyl carbon carries a partial positive charge while the oxygen holds a partial negative, making the carbon highly electrophilic. Aldehydes, being less crowded, are far more reactive than ketones. When a nucleophile like cyanide ion attacks the carbonyl carbon, it forms an intermediate alkoxide which on protonation gives cyanohydrin. For example, cyanide ion reacts with acetaldehyde CH3CHO to form CH3CH with OH and CN attached on the same carbon. This is the classic cyanohydrin reaction. Remember, this addition is the backbone of many organic syntheses, making aldehydes extremely versatile. Now imagine transforming that sharp-smelling aldehyde into something more mellow, an alcohol. Yes, carbonyl compounds undergo reduction easily. Aldehydes reduce to primary alcohols and ketones to secondary alcohols. For instance, acetaldehyde plus 2 atoms of hydrogen gives ethanol, while acetone plus 2 atoms of hydrogen gives isopropanol. The reduction can be achieved with catalytic hydrogenation using hydrogen gas over nickel, palladium, or platinum, or with milder reagents like sodium borohydride or lithium aluminium hydride. There's also the Clemmensen reduction, where zinc amalgam and concentrated hydrochloric acid reduce the carbonyl group to a methylene group, CH2. So, carbonyl groups can be tamed or even erased depending on the reagent you choose.
On the flip side, let's talk oxidation. If aldehydes are left exposed to air or treated with oxidizing agents, they quickly turn into carboxylic acids. For example, formaldehyde oxidized to formic acid. Tests like Tollens reagent and Fehling's solution use this property. With Tollens reagent, an aldehyde is oxidized to an acid and a beautiful silver mirror is deposited on the inner surface of the test tube. With Fehling's solution, the aldehyde reduces copper to ions to a brick-red precipitate of copper-1 oxide. Ketones, however, resist such mild oxidations and require strong oxidants that often cleave the carbon chain completely. This difference is a key diagnostic tool in organic chemistry labs.
Now comes one of the most exciting transformations, the aldol condensation. Imagine two molecules of aldehyde, each with an alpha hydrogen, coming together under the influence of a base. The base abstracts the alpha hydrogen, forming an enolate ion, which attacks the carbonyl carbon of another molecule. The result is a beta hydroxyaldehyde. For example, two molecules of acetaldehyde combine to form 3-hydroxybutanol. On gentle heating, this beta hydroxyaldehyde loses water, giving an alpha beta unsaturated aldehyde, CH3CH is equal to CH-CHO. This reaction is central in carbon-carbon bond formation and explains how simple molecules in nature stitch themselves into complex frameworks. Here's a fascinating twist. What happens when aldehydes do not have an alpha hydrogen? They cannot undergo Aldol reaction. Instead, they participate in the Cannizzaro reaction. In the presence of a strong base like sodium hydroxide, two molecules of such aldehyde react, one gets oxidized and the other reduced. For instance, two molecules of formaldehyde with sodium hydroxide give one molecule of methanol and one molecule of sodium formate. Essentially, it's a disproportionation reaction where the same compound plays both donor and acceptor. This is one of the neatest tricks carbonyl chemistry has to offer. Finally, let's extend the story with cross-aldol condensation. Here, two different carbonyl compounds are used, and at least one must have an alpha hydrogen. A classic example is acetaldehyde reacting with benzaldehyde under base, producing cinnamaldehyde, the compound responsible for cinnamon's fragrance. The enolate ion of acetaldehyde attacks benzaldehyde's carbonyl, forming a beta-hydroxy intermediate which quickly dehydrates into an alpha-beta-unsaturated aldehyde. Such reactions are not just classroom curiosities, they are essential in industry for synthesizing perfumes, flavoring agents, and pharmaceutical intermediates. So, carbonyl chemistry is the foundation of everyday materials around us, from perfumes to plastics. So, students, to summarize, aldehydes and ketones are highly versatile molecules. They undergo nucleophilic additions, reductions, oxidations, Aldol and Cannizzaro reactions, and even cross-Aldol condensations that are central in both lab and industry. Each reaction not only deepens our understanding of reactivity but also links directly to real-life applications, from the fragrance of cinnamon to the silvering of mirrors. I hope this session helped you see how dynamic and practical organic chemistry really is. Until next time, keep exploring molecules with curiosity and excitement, because chemistry is truly the science of everyday life.